Hello everyone. This week we're going to talk about name resolution on IP networks. If there's one TCP/IP application layer service that provides the glue that ties everything together on the internet, it's the DNS. It's the domain name system. And that's because DNS provides the essential ability to convert symbolic domain names, such as Microsoft.com or example.com, into corresponding numeric IP addresses. So we're talking things like 207.46.130.108, or 69.32.148.124, and so on and so forth. And it's when you combine all the DNS databases everywhere that represents the entire mapping of all valid domain names that correspond to valid IP addresses. And these databases are located all over the internet. Now, despite its widely distributed and decentralized nature, DNS works very well and provides a robust, reliable, and stable foundation on which IP address translation depends. It's a profound validation of the quote-unquote internet model, where you have a set of rules and behaviors where information sharing succeeds phenomenally without requiring established centralized controls or governance. So when we're done talking about all the parts of this section, you're going to be able to have a much deeper appreciation of what a really cool and phenomenal accomplishment that DNS represents. So what are the objectives in this chapter? First, we're going to describe the characteristics of the various name resolution protocols. So we're talking DNS and LLMNR. We're going to talk about how name resolution works in IPv4, including the DNS database structure, the DNS namespace, DNS Database Records, a delegation of DNS Authority, and the different types of DNS servers. We're also going to talk about how name servers work. We're going to talk about how name resolution works on IPv6, so the use of AAAA records, how forward and reverse mapping works, the use of source and destination address selection, how rules are organized by the source and destination address algorithms, and the end-to-end address selection process. We're also going to talk about how name resolution is supported in Windows and how host files are used, the function of the DNS Server Service and DNS Dynamic updates, how Windows manages source and destination address selection, LLMNR support, working with IPv6 literal.net names, and the use of peer name resolution protocol. We're also going to describe the common sources for name resolution failure and use common name resolution troubleshooting tools such as Netstat and Nslookup. So, understanding name resolution fundamentals. So, name resolution is the process by which a computer maps the human readable names people give to services, so Microsoft.com or example.com, to the numeric addresses the computers use to identify those services. So before a network device can actually send an IP packet, we have to do name to address translation or resolution. There's multiple methods of doing this. We can consult a name to address file table on a hard drive. We can contact a server that maintains a database of name to address entries, and we can send a network broadcast that requests the destination's computer IP address. So what are network name resolution protocols? These are procedures that govern the rules and the conventions used in manually and dynamically providing for name resolution systems in a networked environment. It also provides the definitions and mechanisms involved in client and server applications that are used in name resolutions. Name resolution has become a lot more sophisticated since the days when technicians and administrators manually added entries to an etc host file on a Unix system or Windows System 32 driver etc hosts on a Windows system. However, you can still do that, and it's very useful, especially if you're building systems or testing systems. So LLMNR, this is your link local multicast name resolution, is defined by RFC 4795, and it's a protocol based on the DNS packet format. LLMNR allows for IPv4 and IPv6 network nodes to perform name resolution for other devices connected to the same local link. And it's ideal for smaller networks and other environments that don't or can't provide DNS name resolution and that require name resolution for both IPv4 and IPv6 nodes. Here in this figure, we're looking at the LLMNR header format, and we're describing the typical message exchange when using LLMNR. So more commonly known is DNS, the domain name system, described by RFCs 1034 and 1035. It's a system used for naming computers and network services using a hierarchical structure for organizing those objects into domains. RFC 3596 describes the DNS extensions for IPv6. DNS and IPv6 extensions for DNS are talked about later on when we look at name resolution in IPv4 networks and name resolution in IPv6 networks. So we talk about RFCs 882 and 883. These are the original RFCs for DNS. Paul Makapetris made this. He also created Jeeves. We also have Bind, which you might have heard of. Kevin Dunlap wrote that in 1988. And Bind was specifically created for BSD Unix, for 3, and it's extremely important when we talk about the back end of DNS. In the database segments, they really only include a portion of the overall namespace that DNS can access for its clients. And then DNS is one of the TCP/IP services. There's a lot of books and articles that have been written on this subject, but when we talk about kind of your career in this, you can build an entire career on DNS if you want to study it. It's very deep subject, very specialized, and it can be extremely confusing to get a grasp on. So when we talk about this, it really is an overview of DNS. So just keep that in mind. I guess following it again, DNS, what does it do? It allows for local control over domain name database segments. Data from all the database segments is available everywhere, and the information is robust. And these need to be adhered to as we're looking at overall how DNS operates in the overall system. But again, just we talk about how it's a confusing and deep subject. This is probably the most effective use of distributed databases you'll see in the world. It has been for a long time, and it still is. And it's what we depend on every day. So the DNS database structure, the root is represented as a dot, and root servers, they're also referred to as dot servers. So it mirrors the structure of the domain namespace itself. So when you think about actual internet domains, .com, .edu, .gov, .mil, .net, .org, these are the top TLDs, so top level domains, if I say the acronym a lot, in the United States. In addition to this, there's a lot of other domain names. Recently, ICANN has started to sell customized TLDs. So we're talking .family, .farm, .vip. You can actually create your own, propose it, and sell it. It costs a lot of money. There's also kind of in between those two phases, there were ones that were created, like for air transport, myindustry.aero. I have matt.aero. .coop for cooperative, .info, which is just informational, .int for international treaty organizations, .museum for museums, .name for individuals, .pro for professionals, .tv. While it's used for television broadcasts, it was originally created for Tuvalu as their country TLD, just like .us for United States. And domain names have to comply with ISO, so the International Standards Organization, 3166. So the DNS namespace. DNS arbitrarily partitions trees and creates subtrees for database information. So IBM.com can be broken out into subdomains like clearlake.ibm.com. in terms of the namespace of domains and subdomains, another way to look at it is that everything to the left of the domain name, quote unquote, belongs to the domain name. So when we say clearlake.ibm.com, Clearlake, everything left of .ibm.com belongs to the domain. And any valid domain ultimately resides within some specific DNS database. DNS Database Records, again, when we talk about RFCs, this is in RFC 1035. What do resource records do? Well, they store data associated with domain names, address records, other data. So most commonly you'll see A records, so address records, canonical name, CNAME, host info, H info records, MX records for mail exchange, name servers. Oftentimes when we're doing domain name validation, so like email, for example, for SPF, Sender Policy Framework, and domain keys, DKIM, you'll use text records, which are more of an informational record on a domain. These are all records that are commonly used. Again, pointer records, start of authority, service location, well-known services. Start of authority record indicates the beginning of a DNS zone's authority. So that would include a bunch of fields: owner's name, who's responsible, the serial number, the refresh and retry intervals, expire time, minimum TTL. And we talked about 4A records, so AAAA records are the same as hosts or A records, except they map the host to 128-bit IPv6 address. So look at delegating DNS authority. The organization of the global DNS database is designed to make it quick and easy for name servers to point to other name servers when the first name servers are either not authoritative for specific subdomains. So much of what is involved in navigating the DNS and domain namespace the DNS servers manage collectively consists of following records that point to specific authoritative name servers for specific subdomains. So there's three main types of DNS servers. You have your primary DNS server, your secondary DNS server, and caching servers. So this can be, I guess, a bit confusing. DNS servers are also called name servers. The distinction between the master and the primary DNS servers can also be confusing. A primary and secondary server refer to a type of zone. A DNS name server that holds primary zone files, and they're updatable, is the primary server for that zone, is the primary authority for that zone. The DNS name servers that hold secondary zone files, they're read-only, and they're the secondary servers for the zone. So you go to the primary first. The primary or master DNS server, it's where those primary DNS database files reside. They are distinguished from other name servers in that domain, and for any DNS zone there can only be one primary server. So when you think primary, it's the first, it has the most authority, it is what is used as the main reference point. Secondaries, think of it as backup, think of it as secondary. They're read only, and they serve a purpose of playing second fiddle to the primary servers. Again, secondary server, it gets its data from the zone from the master server for that zone. When you think of what data is on a secondary server, it always is the data from the primary server. And when you zone transfer, the secondary DNS server gets data for the zone from the master server from that zone. There's also a secondary or slave DNS servers. They provide a backup copy for the domain database for that specific zone. Here's an example. Let's talk about master servers. Master servers are part of the zone transfer process. So for example, if The server chalice receives DNS zone information from a server bool. And the server bool is the master, and the server chalice is the secondary for that zone transfer. So think about it in that perspective. And again, the issue between primary and secondary has to do with zone ownership. While master servers initiate the zone information in the transfer process. And a single DNS server could be primary for one zone and secondary for another zone and a master for both zones. So again, this can get extremely complicated. It sounds extremely complicated. But again, we're just doing an overview here of general DNS. Now finally is caching servers. They store recently accessed DNS records from other domains. A caching-only server speeds access to specific domain names by storing a copy of the backup data locally. Size and internet access volume factors determine if a specific organization should implement separate caching-only servers. Now, while you get a performance improvement, the issue with caching servers is if you're doing fast record changes, they have to propagate to the caching servers. So you wind up in a situation where your caching server could have different data than your primary and secondary servers. So you have to take all that into account. What's more important, performance or data accuracy? So how do domain name servers work? Well, a TCP/IP client is usually some application or service that encounters a domain name, and it needs an IP address for that domain. So when a TCP/IP client uses a resolver to send a name query to a DNS server, that client obtains the address for the DNS server queries from its TCP/IP configuration data. The servers are then queried in the order in which they appear in the configuration files. So in Windows, that's going to be a registry entries. It's a flat file in Linux or Unix. And it starts from the top down. And it walks through the sequence of lookups that produces a reply from whichever domain the name server is queried. DNS servers, again, handle real name resolution. And we talked about the sequence of lookups. So again, if we're starting from the top, the DNS servers get the name from the domain namespace. If the DNS server is authoritative, it provides the data about the zones where it is the authority. When it's queried, any DNS server searches its cached domain name data and will answer queries for which that server is not authoritative, unless that query originates from a root server, and that requires the authoritative DNS server in the zone to respond to the question. When a local server does not have information in its database, or its name cache, or if it's a caching-only server, it might need to turn to find other name servers in the neighborhood. There's no result. The name server sends a request for name resolution to a root server. The root server will locate an authoritative server, but it will always find something. The process will always produce some sort of answer. So a recursive query requires the DNS server to take the responsibility for providing the answer, including contacting other DNS servers, until it can produce some result for the DNS client. You have to have a result. So it's used by DNS resolvers to delegate the first DNS server that they contact to go out and find the necessary address translation. And in the overall DNS server hierarchy, any DNS server can issue iterative queries, but only a DNS client or a root server can issue recursive queries. So iterative or non-recursive queries are issued when one DNS server receives a recursive request. And it does not cause other queries to be issues. The reason is some recursive name queries involve a root server, and the root server always knows how to find whatever DNS server is authoritative for that domain. The DNS server that responds to an iterative query simply passes it along if it happens to already have the resolution in its database. So it really takes little responsibility for producing a result. In a relay race, once the runner of the first leg is handed off the baton, that runner has no responsibility for ensuring the race is completed, and it's the same in DNS. Another example of an iterative query is that of a less than scrupulous student responding to an assignment to do a research paper by hiring someone else to do it. Again, you're paying someone for a result, you're handing off, and you don't care what the result is, you just don't want to do the work. To that end, root servers are responsible for the root, so the dot. As you might imagine, the root server cannot possibly contain all the domain information for the internet, but where it's sitting from, kind of on the top of the world, on top of the mountain, it can see where those main top-level domains can be found. So the importance of DNS caching. Every data in a DNS cache has an expiration value. DNS servers, they cache name and address pairs for addresses they've resolved, and they keep information about name requests that result in error messages. So, I guess here's an example of some non-authoritative versus authoritative queries. So, let's say George needs $5 to buy something. So George checks his wallet, sees if he has any money. If he doesn't, he goes to the bank's ATM to make a withdrawal. So another example would be if a student asks you for the address of a classmate, first you see if you remember and give an answer right then. Otherwise, you have to go check the address book for the information. So again, that is non-authoritative versus authoritative in each of those scenarios. We talk about negative caching. That's referenced in RFC 2308. Caching only servers are by their very nature non-authoritative for a zone. So they're typically used again for large volume. And a caching only server provides load balancing and reduced network traffic, but again, doesn't have that same authority. So DNS configuration files and resource record formats. So domain.dns, these are the files that map host name to addresses. Adder, so address.inaddress in-adder.arpa.dns. That files the map of addresses to domain names for reverse lookup. And every DNS zone file has to contain start of authority and name server records. Records about those host names or addresses in that zone, plus records about host names or addresses for related items in the zone. A records, so address records provide name to address mapping data, forward lookup mapping data. Pointer records provide address to name mapping or reverse lookups, or reverse lookup mapping, so mapping for reverse lookups. The CNAME records allow you to define aliases for your hosts in the zone, and really CNAMEs, it's mostly as a convenience to make that data entry process more efficient in the zone files. So let's talk about the individual records. So SOA, start of authority, that identifies the current name server as the best source of information for that zone. Both secondary and primary name servers can designate themselves as authoritative in their own SOA records. Outside of kind of what's in this chapter, SOA also contains a few other data fields, the owner name, so the host name of the primary DNS server, and the responsible person, which is the email address of the person responsible for administering the zone. So A records and C name records, so address and canonical name records. So DNS, by default, accesses only the first IP address for a host when multiple entries for a single domain are defined. DNS round-robin load balancing permits a DNS server to keep track of which IP address it is provided for a specific translation, and it rotates that IP address within the list of addresses available. So the A record, so the address record or host name record, contains a host or DNS name and associated IP address. It's the simplest and most common record in a DNS database, and a name is required for any host that shares resources on a network. The C name or canonical name record provides an alias for the host name by mapping an alternate DNS domain name specified in the owner field to a canonical or primary DNS domain name. So as an example of a multi-home device, so if you're familiar with your home network, you have a computer with two network interfaces. Each is configured with an address and a subnet mask of a different network. So if you have a home network 10.0.0.0, that's your home network. It's configured on one interface, and a cable modem connection with a routable IP address from an ISP on another interface. This is what's called a multi-home device, and you're very likely to have one of these devices. And we talk about round robin. It's used for frequently accessed services like IIS, so Internet Information Services, web servers. So if a home page is located on several IIS servers, several web servers, you do Apache as well, the same alias can be assigned to all of them. Then all their IP addresses are linked to that alias. So this gives some semblance of load balancing. So mapping addresses to names. So records in the db.adder file, they're provided to support reverse DNS lookups. And reverse lookups are used primarily to determine if IP addresses that user presents matches an originating domain name. The file structure of a reverse DNS lookup is classful, so the files have to follow the logical subdivisions of IP addresses into classes A, B, and C. So name resolution in IPv6. Now we're back into IPv6. DNS still operates in IPv6 environments. By that extension, that means that DNS has to operate in hybrid IPv4 v6 environments, because side-by-side operation for IPv4 and IPv6 networks, it's going to happen for the foreseeable future. The basic mechanisms of DNS continue to be unaltered in the IPv6 implementations, but the task of name resolution is a little bit more complex because of the multiple addresses that IPv6 hosts and interfaces can own. IPv6 offers a backup service that can stand in for DNS that's not offered in IPv4. And the LLMNR protocol uses the same message format that conventional DNS uses, but it runs on different ports. So it was originally defined, so we're talking about DNS for IPv6 in RFC 1886, but it was superseded by RFC 3596, and it defined the DNS extensions supporting IPv6. So the Quad A or the AAAA record was developed to accommodate larger IPv6 addresses, and IP6.int was created. Now it's IP6.ARPA to support IPv6 reverse mappings. And then forward mapping involves sending a request to a remote host with its domain name and requesting its IP addresses. So we have a few diagrams here. First is an example of a AAAA or quad A record for resource. In the middle figure, figure 8.4, we see a single DNS entry for a domain with multiple records. One is a standard address record, so an A record with an IPv4 address, but then we see a quad A record with an IPv6 address as well. And in lower figure 8.5, we see a sample of IPv6 reverse mapping zone files, and they're using the origin control statement. So the source and destination address selection process, it's specified in RFC 6724. So the name resolution process for IPv6 is more complex than IPv4 because IPv6 addressing allows multiple unicast addresses to be assigned to a computer's network interfaces. These addresses can have different reachability scopes. The scopes can be link local, site local, and global. For an IPv6 node with multiple addresses assigned to an interface, multiple IPv6 addresses are returned in the DNS name query response message, making the selection of the source and the destination IPv6 address more complex. The source and destination address must be matched to each other for both the address scope and purpose. So we're going to talk about first the source address selection algorithm. So here is an example of a default policy table on Windows computers, on Windows 10 computer. So here's the algorithm, and these are processed sequentially. So rule 1, you're going to prefer your source address that equals the destination address. Next, rule 2, you're going to prefer the source address that has the appropriate scope for the destination address. Rule 3, you're going to prefer addresses that are not deprecated. And rule 4, you're going to prefer a home address. So this is in there for IPv6 mobile. And rule 5, for routers, you're going to prefer some source address that is assigned to the next hop interface, pointing at destination addresses. Rule 5.5, for routers, you're going to prefer addresses next in a prefix advertised by the next hop. Rule 6, next down the list, you're going to prefer source addresses that has the same label in the prefix policy table as the destination address. Next, you're going to prefer a source address that uses a temporary address over a source address that uses a public address. And finally, you're going to prefer a source address that has the longest matching prefix with the destination address. And here is an example about all the rules in a single flow chart. This is the source address selection algorithm. Next, we're going to talk about the destination address selection algorithm. So again, just like source, these rules are processed sequentially. So rule 1, the first rule, prefer a destination that is reachable over one that's not. Second, prefer the destination that matches the scope of the source address. The third rule, prefer a destination address with a source address that is not deprecated. Fourth, prefer a destination with a source address that is a home address. So again, this goes back to IPv6 mobile support. And rule 5, you're going to want to prefer a destination address that has the same label from the prefix policies table as its source address. In rule 6, you're going to prefer a destination address that has the highest precedence in the prefix policy table. Next, you're going to prefer a native IPv6 destination over an IPv6 transition technology destination. Next, you'll prefer a destination address with the smallest scope. 9, you'll prefer a destination address possessing the longest matching prefix length with its source address. and 10 otherwise. You're going to leave the order unchanged. So when you're using address selection from end to end and operator on node 1 queries a remote host for its configured addresses, the remote host is going to reply with multiple addresses, and node 1 then uses the source address selection algorithm, and following that, node 1 uses the destination address selection algorithm. So the application on node 1 is provided with the ordered destination addresses and related source addresses. And then the application will attempt to use the source and destination address pairs until it successfully establishes communication. So if you're looking at changing the address scope preference, the destination address scope preference, you're going to look at destination address selection algorithm rule 8. And that gives preference again to the destination addresses with the smallest scope. And you might want to change the policy table to reverse the default preference. So in Windows, it would be netshell, so netsh, interface, IPv6, set prefix policy to change the default order in which address scopes are sorted. Network basic, so name resolution support in Windows operating systems, NetBIOS, so network basic, input-output systems, and WINS Internet Name Service. These are historical and native name resolution methods for Windows, but the technologies are pretty much, not completely, been made obsolete by DNS. So what's a DNS resolver? DNS has two basic components, the server component and the client component. So on the client computer, the DNS name resolver is responsible for initiating and sequencing DNS queries that result in name resolution for an application running on a computer. And there's two types of queries, a non-recursive query to a DNS server, and then finally a recursive query to a DNS server. So let's look at the client side of DNS. A name resolver, also called a resolver, it's a piece of software on a client computer that accesses the DNS domain servers. Resolvers issue requests for service called name queries or address requests to domain name servers. And the majority of DNS queries that are sent are name queries. The address request that seeks to resolve a domain name to a corresponding numeric IP address, and a name query or an inverse DNS query seeks to resolve an address to a domain name. I guess if you've ever seen invalid domain name error messages in a browser, it probably happened to everybody. Usually because you mistyped a domain name, misspelled it. Try that out. This is an example of how browsers interact with the DNS resolvers. And here is a screen grab of a client-side DNS, the output of a resolver cache. So the DNS Server Service, older Windows servers, Windows NT, etc., relied on NetBIOS and WINS. Windows Server 2003 through 2016 and higher depend on DNS. So Windows Server 2012 machine configured for the DNS server role offers IPv6 support, which gives you a longer address space, background loading of zone data, read-only domain controllers, and global name zones and global query block lists. Windows servers also support stub zones, so they're copies of a zone that contain only the resource records, and the DNS Server Service on Windows supports incremental zone transfers. So you might have heard DDNS oftentimes on Home networks, your IP addresses changing on a regular basis, especially older style networks like modems or DSL, where we've talked about this in some of the other chapters. Your IP address might regularly change. You might have low lease times. This is where dynamic DNS comes into play. It allows for automatic machine registrations and record updating on DNS servers, and it's fairly straightforward from a high-level viewpoint. Step 1, a client computer sends a DNS query to locate an authoritative DNS server. Step 2, the local name server responds with the IP address, host name, and zone name of the authoritative DNS server for that zone. Part C, the client computer attempts to dynamically update the authoritative DNS server. And last, the authoritative DNS server replies with either a success or a failure message. So, source and destination address selection. When a Windows computer has more than one IP address configured for network interface, the TCP/IP stack will choose one unicast address to use as the computer's source IP address. This complies with RFC 6724. Windows 7 computers, when we're not talking about the IPv6 readiness update, support IPv6 destination address selection as defined by RFC 3484. Windows 8 and later, Windows 7, Windows 2008 R2 with the IPv6 readiness update support RFC 6724. So we've already discussed LLMNR and its main features. When we're looking at LLMNR in a Windows environment, it's enabled by default. So it's supported in Windows Vista through Windows 10, Windows Server 2008 through 2016, and so on and so forth. And on client computers, it attempts to research for a domain controller DC on that domain. And it can be disabled either by using group policy in Active Directory or the registry on individual computers. So when we're working with IPv6 literal.net names, these are supported by Windows Vista through Windows 10 and Windows Server 2008 through 16, and they can be used by applications and services that are unable to recognize the syntax of IPv6 addresses. RFC 2732 provides generic syntax for URIs, ORIs, and addresses. Microsoft Windows IPv6 proprietary peer-to-peer name resolution protocol system. This is what we're looking at when we're talking about the peer name resolution protocol. Peer names published in the PNRP clouds, they fall into specific groups depending on the scope, either the global cloud, the link local cloud, or the site-specific cloud. And here is an example of a PNRP ID structure. So when we're looking at troubleshooting name resolution protocols and failures, there's a few shortcomings with DNS. So database updates usually require a qualified administrator or special purpose tools. There's a propagation delay. The knowledge it takes to manage DNS in the network is extremely involved. It takes a great deal of time and expertise, and it might be relatively expensive for an organization to pay for a person with highly specialized knowledge to run DNS servers. We're going to talk about a few things. Active Directory, again, if you're familiar with Windows servers, DDNS. When we talk about Active Directory, propagation delay can be seen in Active Directory, routing table updates. Any system where a group of devices must dynamically share the same information and have the same map. It could take as much as 3 days for name-to-address translation to become completely effective on the internet. Typically, it occurs within 30 minutes to 48 hours. There was a great example before of Amazon and eBay running into this. And then also the bandwidth and speed of transmission channels. It's going to take longer to update a DNS server that resides on slow or narrowband WAN links that communicate over on a smaller bandwidths. Common sources of failure here. So, two common sources of name resolution failure are negative response to a query and positive response to a query with an incorrect name. When we get a negative result, some of those common causes are incorrect domain name suffixes appended to a query name, incorrect IP configuration on a client or server, querying a name server that is not authoritative, or an inability to connect with the correct name server. When we have a positive but incorrect name server, a lot of times it's incorrect data stored in a name server's resolver cache. The process for troubleshooting DNS on IPv4 versus IPv6 is essentially the same. Again, the key differences are knowing how to specify an IPv6 name server and knowing how to format forward and reverse mappings for each IP version. So Netstat shows active TCP connections, listening ports, Ethernet stats, IPv4 and IPv6 stats, and it's available on Windows, Unix, Linux, Unix-like computers. Here is an example of common Netstat command parameters. Nslookup is another common tool. It's supported by Windows and Unix and provides access to all kinds of DNS information. And it's an essential tool for testing when configuring or troubleshooting a DNS server. So, for example, you would type in Nslookup and a domain name like Microsoft.com to run the tool. And here's an example of the Nslookup command. Here's the help screen for Nslookup. The set option command in Nslookup is used to examine specific types of resource records. And the ls-a switch or the ls-d switch, they're used to extract information from certain well-known name servers. So here's an example of examining NS records for edtittle.com. And here's an example of Nslookup error message. And here's the example of output for Nslookup for an IPv6 host name. All right, in summary, the domain name system gives you key address resolution services that make today's internet possible. DNS name servers come in multiple varieties. We talked about them. It can be confusing. Go over it again. Read the book. For each zone, a primary name server is mandatory. DNS maintains its data on a large collection of name servers all around the internet, all around the world. DNS databases consist of a collection of resource records. DNS clients rely on resolvers to interact with available DNS servers for name resolution services. DNS packet structures incorporate type information that identifies the kind of resource record being carried. IPv6 networks use DNS extensions but must be able to work in hybrid v4, v6 environments. IPv6 source and destination address selection is managed by algorithms that use a set of rules. Windows operating systems support both DNS and LLMNR. Common causes of name resolution problems and failures: user error, just kidding, hardware or network problems, and misconfiguration of FQDN, fully qualified domain name suffixes. That's all for today. Have an excellent week.